Okay, good morning. This is Professor David J. Pilos Reyes. Okay, it's October 12, 2023. The time is 5:30 a.m. Okay, my topic for this session will be college algebra, the last part of college algebra. I'm almost done with the college algebra. The discussion for tonight will be on partial fractions, and this will be under case number 3 under partial fractions. That is the so-called denominator of the fraction will contains quadratic factors. It's not repeated, it's only quadratic factors. Okay, let's proceed. This is now college algebra, lesson number 88. The subtopic will be partial fraction. Under case number 3, the denominator of the partial fraction or the fraction in which we are going to find the partial equivalent. It is just simply quadratic factors. Okay, let's try to bring out the form and how to simplify if the given denominator of the fraction contains quadratic factors. This is the sit-up form. F1x all over F2x, this should be equal to. The right-hand side is a little bit complicated compared to the so-called linear factors or repeated linear factors because we are now, the equation now involves a quadratic equation. The right-hand side will be this, a unknown constant a multiplied by the quantity 2px plus q, close quantity. The given denominator will be a px squared plus qx plus r plus another constant b over px squared plus qx plus r. These denominators are the same. So for quadratic factors, there will be no problem adding the right-hand side because this is the same, right? But with regards to the numerator, this is a multiplied by 2px plus u, close quantity. This is only plus b. So meaning to say for each quadratic factor, the equivalent on the right-hand side will be this. There will be two unknown constants a and b. So to take the equivalent of the given fraction which contains a px squared plus qx plus r, it will be this. A multiplied by the quantity 2px plus q, close quantity, over the given quadratic factor, plus another constant b all over the given quadratic factor. Okay, I will show you the significance of these quadratic factors because when we reach integral calculus, there will be integration problems, okay, in which it cannot be solved by other solutions except the so-called converting it first to the so-called quadratic factor equivalent. Okay, let's try to bring out an example problem. The example problem will be this. I will correlate this algebra problem to the integral calculus problem. So when you reach integral calculus, you know what you are doing and you know how to apply the importance of partial fractions involving quadratic factors. The given equation will be, or algebraic expression is x squared over x squared plus 2x plus 2, and this should be equal to. What will be the partial fraction equivalent of this one? Actually, this problem actually came from integral calculus. There was an integral sign over here, and there was a dx over here. And the problem is asking what will be the integral of x squared dx over x squared plus 2x plus 2 equal to. Under this study of algebra, okay, we don't have the integral sign. I'm just correlating later on that with this type of problem, okay, it will point to the problem under the so-called study of integral calculus. So because to integrate this one, if we are now on the integral side, we must have to take the what you call this quadratic factor equivalent that is on the right hand side of this one. We will convert this one to this form here. So if we try to integrate, Okay? This is an easy one already. Because if we try to take the first derivative of this, it should be 2px plus q multiplied by 1 or simply q. So it seems that this is du and this is u, and this now falls under the natural logarithm of u. Right? We are not yet on the conversion of the, what you call this, quadratic factor. I'm just showing you what will be the significance of this one. Why there is a 2px plus q over here. Okay? Because we are anticipating a problem that we will be solving the integral of a du over u. Okay? This is u, this is du. So if we could find for a, this is now integrable. Okay? And for the second one, there's still a problem because it's still a quadratic equation. But if we could solve for the value of b, we can find for the integral of this, okay, as long as we know the value of b. Okay, I will try to remove the integral sign. So that's the significance of this, what they call this, partial fraction and the quadratic factors. Okay, let's try to solve this problem here. We will take the so-called partial fraction equivalent. The given denominator is actually x squared plus 2x plus 2. So it falls under quadratic factors. Right? What I did first is that this is x squared, this is x squared. I long divided. So what comes out, there is an exact quotient of 1. And the remainder will be a 2x, quantity 2x plus 2 all over x squared plus 2x plus 2. So there will be no problem with this one. So our only problem now is the equivalent of this one. Right? And it falls under partial fraction involving quadratic factors. Okay, let's try to bring out the equivalent of this one. We neglect first the negative sign for the meantime. I will just take 2x plus 2. So this 2x plus 2 over the given quadratic factor. So this is now f1 of x. And this is now f2 of x. This is. Right? It falls under quadratic factor. So if we try to take the linear, what you call this partial fraction equivalent of this, we'll follow this one. There is only one quadratic factor, so there will only be two fractions on the right. It will be a multiplied by the quantity 2x plus 2 over x squared plus 2x plus 2 plus another constant b over x squared plus 2x plus 2. This one, I follow this one because this is the general concept and how to take the partial fraction equivalent if the function f2 of x is actually a quadratic factor, meaning a quadratic equation. Okay, simplifying the resulting equation now, I will rewrite the left hand side. For the right hand side, we can compress now, right? This is denominator of the first one. This is the denominator of the second one. They are the same. So if we try to add this one, we add the numerator. Okay, we add all over common denominator. I will place this in the quantity so we can cancel. Right? So after the cancellation, it seems this is now 1, this is 1. Okay? So no more denominator, right? So what comes out will be a 2x plus 2. Okay, we expand this one now, a 2ex plus 2a plus b. So this will now be the resulting equation, okay, needed to compute for the value of a and b. Like what we did the last time around, we assume a certain value of x to eliminate the other one, but since this is just a simple one, we can just equate coefficient of like term. So we will start, the highest power of x here is actually 1, right? So x to the first. So equating coefficient of like terms for x to the first power or just simply x. For the left hand side, okay, there is a term that contains x and the coefficient is 2. And this should be equal to the right hand side. The term that contains x, okay, is this function here, and the coefficient is 2a. So 2 is equal to 2a, therefore a now will be a 2 over 2, or a will be equal to 1. Okay? For the x to the 0 or all pure constant terms for both the left and right, it will be x to the 0, right? Meaning constant to the left will be equal to the constant to the right. For the left hand side, it will be 2, the pure constant. We are done with this, right? So we'll go to the constant. Right hand side, we are done with this. 2a is a constant, b is a constant, so this will be equal to 2a plus b. So 2 will be equal to 2. What is a? We computed for the value of a times 1 plus b. So b now will be equal to 0. Right? B now will be equal to 0. Because b will be 2 minus 2 if we transpose, therefore b will be 0. So rewriting the given original fraction, that is 2x plus 2 over x squared plus 2x plus 2. Quadratic factors, right? Right? And they should be equal to, I am following this. The value of a is 1 multiplied by the quantity 2x plus 2 over the given quadratic factor plus the value b. The computed value of b, where's b? B is 0. So this is 0 all over the quadratic factor x squared plus 2x plus 2. But a 0 all over anything, it will still be 0. So actually this will disappear. Right? So it seems, what comes out? A 2x plus 2 over the quadratic factor is equal to 2x plus 2 over the quadratic factor. So meaning after following this concept here, it comes out that the given fraction is still equal to the equivalent fraction. So if we now try to integrate this one, you put a dx here, okay? This will be our u. So our du, okay, this is now differential and integral calculus. Du will be 2x plus 2, okay? This is multiplied with dx. So this one here is actually the product of this, right? Exact. So if we try to integrate this one, this will be the integral of du over u. And this should be equal to the natural logarithm of u. So after the converting the given partial fraction to its equivalent, what comes out? It's still the same. And we could integrate now. And this now falls under the integral of du over u. Right? So if we go back to the original problem, if we are now on the integral, okay, this one here, if we put the integral, it should be x squared dx over this. After the long division, there is a perfect quotient 1, so this is 1 minus the equivalent of this. So if we try to expand, this will be the integral of dx minus the integral of this one is 2x plus 2 times dx, this preceded by negative over x. Like what I said a while ago, this is du, and this is u, and this falls under the integral of du over u, and this should be natural logarithm u. So the integral of dx will be x, and the integral of this, the integral of du over u is natural logarithm of u, natural logarithm of the quantity x squared plus 2x plus 2 plus c. The subject matter actually jumps from algebra to integral. I am just what you call this explaining the reason behind why we need to convert that partial fraction. So if there is a problem in the integration in which it is not solvable by other problems, we could solve it by using partial fraction under quadratic factors. Okay, that's it, guys. Good morning. This is Professor David J. De Los Reyes from Los Angeles.